All right, so how do we make alkenes? Been there, done that, right? Let's just run it through real quick. We have some alkyl group with a leaving group, and we hit it up with a base, or we can actually do it in a lot of ways now, right? So let's say our leaving group is OH. We know acid can do the job. Let's say it's OTS, or a tosylate or X or some good leaving group, then we know we can hit it with base, right, to do an elimination reaction. So that's pretty much the preparation of alkenes. We've been doing that since chapter 8, the elimination reactions, and we kind of touched up more so on the dehydration reactions of alcohols in the next chapter. And so we're pros at that by now, but just a little reminder, just in case you forgot. But addition reactions. So that's what do we do with these alkenes once we have them? Well, we can add stuff to them across that pi bond because that pi bond is easily broken. We can manipulate those electrons to create new chemical bonds and new chemical bonds to X and Y. So let's say we have wedges and dashes implied right here. So we can add X and Y kind of across from one another, or we can add X and Y more or less along the same side of that double bond. Okay, so this is pretty much just kind of vocabulary what we're going over right now. We'll get into the details later, but notice the different orientations of X and Y. This is not a result of bond rotation, but a result of the way we added X and Y. Anti-addition is the first one in red, and syn addition is the second one in blue. So syn meaning the same side and anti meaning the opposite side. Okay, pretty straightforward stuff so far, right? Good. We're cruising. All right, so now you don't want to watch me draw all this stuff, so I like this song. That's the jam. Now, by the end of this, you will be able to draw the products, basically filling out this chart. But first, what we want to do is go over that first one, which is the addition of HX. Okay, and so you do have access to that PDF file, so you will be able to fill it out again, and it's really important that you understand what the products are, but also how you get to those products. So as I said, addition of HX, hydrohalogenation, also known as electrophilic addition of HX. Okay, so we'll say what now? That is not a rectangle. Oh my goodness. All right, so let's say we have an alkene and we have HCl. Well, what we're going to end up getting is the addition of H and Cl across that double bond. Okay, it's pretty straightforward, right? Now, remember, alkenes are electron rich, and so they are Lewis bases, and therefore they can be nucleophiles. And then we already know acids are acids, right? Lewis base, or Lewis acid, or Bronsted acid in either sense. Okay, so if we have a Lewis base and we have a Lewis acid, let's jam the two together, right? So the pi bond essentially can swoop on that proton, and what that does is that breaks that pi bond, leaving the carbocation intermediate, which is susceptible to nucleophilic attack by the conjugate base, which is also a good nucleophile. So, carbocation intermediates, come on, those guys do all kinds of weird things, right? We want to take a look at that methyl cyclohexene though to really understand, because we want to fill out that chart, right? So methyl cyclohexene makes it more interesting because now we don't. On the above regular just cyclohexane, or I'm sorry, regular cyclohexene. We had a symmetrical compound. Now it's unsymmetrical, so we get the chlorine maybe added to where the methyl is, or maybe that chlorine adds to the CH2 portion, all right? Or I'm sorry, that secondary carbon, right? And so this is where hydrohalogenation gets interesting. Remember, all right, so we highlight that H in blue. We're explicitly drawing that one just to follow where things go, but we also want to keep an eye on that nucleophile, right? So where's the nucleophile going? It's actually not going to go to the we're not making the compound on the right. We're only going to make the compound on the left. Now, that is it. We have to take a look at that carbocation intermediate to better understand why this would be the case, okay? So, let's see. We got, after the addition of a proton to that methyl cyclohexene, right? We can form, it could either be added to where the methyl is or to the other side, right? If we add it where the methyl is, then we're going to end up with this secondary carbocation right here. If we add it to where that on the bottom, then we would get a carbocation where the methyl is, which, take a little look, see, that's a tertiary carbocation, right? What do we know about stabilities of carbocations? Secondary sucks. Tertiary's better. So the chlorine or chloride adds to that tertiary carbocation, therefore giving us one final product, okay? Now, don't just take my word for it. We have to apply it to kind of what we know. And so when we look at the energy diagram, we can better understand why this might be the case in terms of like how the reaction could proceed, right? A lot of people always ask me like, how does it know, right? Well, how does it know that it's going to be more stable when it gets there? How does it know anything, right? Well, this is a two-step process, right? So addition of that alkene is the energy diagram is going to look like this. We're going to get have this transition state. Number 1 is what I'm going to call it to indicate the addition of that proton, right? Or the process of adding that proton. Now, if we say that we're adding it to the bottom carbon, that means we're getting partial bond formation of that carbon-hydrogen bond, partial bond breakage of that HBr, as well as partial bond breakage of that pi bond, right? We have the partial charges as well, okay? And then the intermediate product is the tertiary carbocation, right? Now, we have a second transition state for this two-step process, and that is basically just the partial bond formation between the carbon and the bromine, okay? And we will also have our delta positive and delta negative charge on the carbon and bromides, respectively. Okay, so what do we know about stability or energy diagrams and with respect to kind of final products? Well, we do know that Hammond postulate says that in an endothermic process, which is that first step, it's endothermic, the product, if it's closer in energy to the transition state, then the transition state looks more like the product, right? And so this is exactly why we form that more stable carbocation in that single product with the chlorine or bromine at the methyl position. Because if we had the secondary carbocation, then the intermediate energy would be higher, and therefore the activation energy would be higher for that higher energy transition state. And so that means that since the activation energy is lower for the tertiary carbocation formation, that means that rate of reaction is going to be faster, and we're going to get more of that product, and more than likely just all of that product, just because of the differences maybe in the activation energy. Okay, so remember the Hammond postulate. You got to remember that stuff. It applies for now and forever. Okay, so this also leads us to Markovnikovs rule. Okay, so Markovnikovs rule is when we're talking about electrophilic addition, in this case of like HX, in an unsymmetrical alkene. So that means we have maybe 2 sites that we can add it, okay? Or there are 2 different possibilities that we can add these, the hydrogen and the X. Then Markovnikov's rule says that we will get the hydrogen atom added to the less substituted carbon, while the X atom is added to the more substituted carbon. Okay? Or in other words, what we can say is basically the hydrogen atoms go where the hydrogen atoms are, right? So, or rather, if we take a look at let's see, where is it? Let's draw it on this particular compound. We have a pink hydrogen and no hydrogens where that methyl is, right? And then the product, the carbocation intermediate, we have a pink hydrogen and then that added blue hydrogen. Okay, so what I mean by that is the hydrogen went where there were more hydrogen atoms. Okay, so that's another way of thinking of it. So put the hydrogen where all of the group of hydrogens are, and then you're good to go. Okay, so that's just another way of saying that you add the hydrogen to the least substituted carbon, because that's coincidentally the same thing. Okay, and this is again, Markovnikovs rule real quick is regioselective, or implies regioselectivity of the electrophilic addition. Okay, now the stereochemistry of the electrophilic addition is a little bit different. Okay, so we shouldn't be able to anticipate the stereochemistry because we're super awesome and we understand mechanisms and the possibility of attacking from the top or the bottom when we have a carbocation intermediate. Okay, so what that means is, in this case, we will get addition of the chlorine in the form and visually we'll have it as a wedge or a dash, but now in this case it's samesies, right? Same compound, but if we have an unsymmetrical or something else that has like some stereochemistry applied to it, like this methyl with a wedge on it, if we add HCl, now what we get, still getting the chlorine as a dash as well as the chlorine as a wedge at that same position. Okay, but now the relationship between these two compounds is no longer that they are the same, but if we take a look, we can quickly identify that these are two stereogenic centers, and then we can say that these are the same stereogenic centers but different orientation around that stereogenic center on the right. So since we swapped one configuration, then that means they are diastereomers, okay? Because the other configuration is the same. It could be S or R, it doesn't matter. We don't need to take the time to do that. We can just look at it quickly, right? So again, the reason why this happens is because that carbocation intermediate is planar and you can attack equally from the top and the bottom. So don't forget about the rearrangements as a possibility, because we do have those carbocation intermediates. Those will bite you in the booty. And then Markovnikovs rule, that means that this particular reaction is regioselective, okay? Because we are forming one specific product when we have two possible sites of adding that nucleophile or regions on that molecule, right? That's why it's called regioselectivity. And then syn and anti-addition is due to that planar carbocation. Okay, so again, just reiterating myself, but I want to really hammer it in there so that way you get a good understanding of the process. Okay. All right, so this was one of many reactions that we saw on that super awesome chart that I started for you. The next one that we're going to go over in another video is the hydration. So basically electrophilic addition, but addition of water. So we're going to get this methyl hexene, cyclohexene, and we're going to get addition of OH, but we got to see how we do that and all of the little things we got to watch out for. So check out the next video.